Time to start. So the plan of this lecture is written here. It looks long, but I hope to just spend a little time on each of them. So this is going to be an introductory talk about tensor rank. And I'm selecting the topic, I really made sure that I don't touch or I don't use or I don't mention even anything from algebraic geometry or representation theory that do go into some of these investigations. So it will all be just linear algebra and some combinatorics. The main reason is that I want to talk about it is that there are some open problems that I really want to think about. I thought about some of them in the past. I want to think about them now. There are several people here that are interested in them, and the next 2 Tuesdays, Jeroen will give lectures on related topics to tensor rank, asymptotic tensors, and other things. Yeah, so everybody who's not already doing this should join us. Okay, so tensor rank is, so what's a tensor? A tensor will fix a field F. Usually you can think of it as C. It's interesting for every F, lots of the questions. Sometimes we know things just for large fields F. Anyway, the D, which is a number of dimensions. And then we are looking at what's a tensor? A tensor is, you can think of it as an element of, and we'll fix n, although you can think of, these are parameters. And you can think of it also as a function from, that's right. Okay, so it's just a d-dimensional array, n by n by n by n, full of numbers from the field. Okay, and we want to know its rank. So let me tell you what's a rank 1 tensor. So rank 1 tensor is that I'll define the rank of this that's the definition. Okay, well, unless they are always, one of them is 0, then, so these are vectors. Right, so the tensor product of linear forms is just rank 1, and then you define the rank of any tensor. The rank of T is simply the minimum k such that T equals T1 plus Tk. Maybe I should call it R, because this will be a good name for rank. And the rank of Ti is 1. Okay? And there is a related notion that I'll define now, and I'll talk a little bit well, let me talk about it when I get to border rank. So just so the definition is clear. I give you a tensor. I just give you explicitly this array. What's the rank? Okay, so that's a basic question we are interested in. That's a computational question. Or alternatively, you can say structural. You want to characterize all the tensors of rank R. And let me tell you just the basic things we know. Okay, so given T and also find tensors of high rank. So this one question, and find T of high rank. So when these two, we know everything. These two is just matrices. Matrix rank is completely understood. Matrix rank in particular has nicer definitions than this. This is more or less a definition by a complexity measure. It's a minimum number of simple things you can add up to get something. But you know, we know a lot about matrix rank. Linear algebra is efficient, so we can find out the rank of any tensor. We know tensors of maximum rank, the identity matrix, and so on. So this is easy. And everything starts for us when d is bigger than 2 and things become complicated. So the first, regarding the first question, complexity-wise, there is a result of Hastad from about a decade ago, 15 years ago. So we can forget about this, and we are just computing tensor rank NP hard. This is true over every field. In over finite fields, it's NP complete because you can also check the rank. But anyway, it's hard. So we are not going to do it simply. We'll talk about special cases later. Now I want to talk about the ballpark in which these tensor ranks live. So there are some obvious things. One is that, so if we fix this, so the rank of a tensor T, so we fixed D and N. That most n to the d minus 1. Everybody sees this? It's just like the rank of matrices is at most n. When you write it in this decomposition, you can take all the way up to here basis vectors, and here take whatever linear function, whatever row you find in your tensor. So it's at most n to the d minus 1. On the other hand, for most tensors, so it's not far from the truth. There are better bounds. I'm telling you just a basic thing. For most tensors, it's at least n to the d minus 1 over d. The way to read this really is n to the d over dn. Or that's the way to prove it. How do you, where does it come from? It comes from the obvious thing. This is a number of free parameters in a general tensor. And this is the number of free parameters in this product of linear functions, right? A description of these dilinear forms. So, you know, knowing this, you can prove it over finite fields. It's a counting argument over, you know, fields of characteristic 0. You need a dimension argument, slightly fancier, but not difficult at all. Okay, so we know that most tensors require large rank, and the usual question in you know, computational complexity is you want explicit tensors of high rank, right? You want to exhibit a hard function. You want lower bounds for explicit objects. I'll mention soon why in the applications, but I mean, it's sort of a basic question. You know, I give you a 3 tensor. I mean, can you produce a 3 tensor over any field you like whose rank is bigger than n? There's an easy way to get a lower bound on an explicit tensor, and this is a flattening. What's a flattening? You can always take a d-dimensional tensor and make it into a matrix, right? Just take some of the coordinates, put them in the rows, some of the coordinates, put them in the columns. So you can always transform a tensor, a d-dimensional tensor into a matrix simply by putting here n to the d over 2. Right, let's say the left half, and here n to the d over 2. Now it's a ceiling. Okay, so you just take this high-dimensional array and you compress it, flatten it in any way you like. I mean, take some subset of the coordinates here, some subset of the coordinates here, and of course, the rank of this object is lower than the rank of this object. If you have a decomposition here to rank 1 things, it translates to rank 1 matrices. So every rank 1 tensor by this mapping translates to. So if you want a high dimension, if you want a lower bound on the rank of T, what you can do is take this You can take this diagonal matrix, and you can immediately, and of course it's projection back. It's is a tensor, an explicit tensor. I just described it to you. And the rank of this T, so this is explicit, is at least, or is exactly n to d over 2. This type of operation is called the flattening. This is the flattening. It's just you. And you don't have to do it the way I did it. You can take any linear map. You can just take any linear map from tensors to matrices, and you get this. So it's a method to get lower bounds. In fact, it's sort of almost the only method we know. And we'll see towards the end of the talk that this method, which is really in wide use in algebraic geometry, cannot yield much better bounds than this trivial, stupid bound. It's amazing, but it can. So that's when we get to barriers. OK. Notice that in the case of d equals 3, then this bound is just n, which is sort of the absolutely trivial bound. So we will be fighting to improve this. OK? Let me mention just a few motivations, and quickly. I mean, there are lots of motivations to understanding tensor rank. Any questions? So it's all as a, yeah.
Is the theory over power d equal power of 2 easier than?
No.
No?
No. Not that I know. No. 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 I mean, for power of 2, there is no ceiling there. So a 4 tensor, you can flatten it into a 2 tensor without losing this, and then you get n squared, which is a trivial bound. Right? A 4 tensor. Right? What?
So for 3 tensors, you can get slightly better.
Yeah. For 4. Yeah, we don't even know that. Yeah. But I'm just saying getting this bound is, yeah, you don't have this rounding. OK.
No, a 4 tensor with rank n cubed.
No, we don't even know a tensor, a 4 tensor with rank 2 n squared. It's pathetic. Yeah, so that's yeah, there's room to do things. OK, let me mention just some of the motivations that are written here. So I mentioned arithmetic circuit complexity.
Maybe you can say that you can, over big fields, you can take tensor with algebraically dependent entries, and those are kind of explicit.
They are not explicit. I don't even want anybody to think they are explicit. They are not explicit. Explicit are, something that you have an algorithm to generate. So, OK, don't listen to him. So very briefly, circuit complexity. Tensors are polynomials, right? One way to think about tensors is just as multivariate polynomials, and you can, and we'll actually do this later. So another way to think of tensors here is just as you have a bunch of n to the d variables, and you just think of a tensor t of these n to the d variables as sum of t I1 id times x1 I1 xd id. So these are multivariate polynomials. That's another way to describe it. And we want to understand the complexity of these objects, and we want to understand it as complexity as, you can think of a circuit computes it, and the circuit is allowed to do, just products of linear forms and then add them up. Then you get exactly the rank is a complexity. But it's a very simple model, and one result, we are trying, so a big part of the field is, maybe I should say, algebraic complexity here, algebraic circuit complexity. Is trying to prove lower bounds for computations over fields, like you are allowed to use addition and multiplication. You want to say that you require many operations in order to compute some polynomial. That's a very basic model to compute very simple polynomials. But you can look at more general ones. You can look at just formulas or circuits to compute polynomials. And one result that's really interesting, there are many, but the one result that's really interesting is a result of Ran from about a decade ago, showing that lower bounds, high enough lower bounds, explicit lower bounds on tensors actually imply lower bounds on much more complex models like formulas. And it proves that if you have an explicit T, so the rank of T is sort of almost a tight bound, what we expect from random tensors, so n to d1 minus d low 1. And if you do it for a range of d, so d is not constant, and d is at most something like log n or log n over log n. Anyway, you are able to prove explicit lower bound for tensors. This will imply explicit polynomials with super polynomial lower bounds, size lower bound. So it's really important to prove this for things we want to understand in arithmetic complexity.
So the same polynomial?
What?
This polynomial?
Not quite. Yeah, I mean, roughly the same polynomial. Yeah.
What did you write the d? D is between?
Between is non-constant and is at most log n or something like this. Log n over log n. Doesn't matter. It's a beautiful paper. It's basically a homogenization result for formulas that's non-trivial. Anyway, that's one motivation. Another motivation is matrix multiplication. The most famous tensor is a matrix multiplication tensor. Now, why is it a tensor? We are thinking about multiplying two matrices, right? We are thinking of AB, IJ is the sum over K, AIK, BK, J. That's the formula for matrix multiplication. So where is the tensor? It's a bilinear map, right? So it's really, if you think of it in terms of a circuit, in fact, what's called a bilinear circuit. So you have the A's here, all the A11, and whatever it is. Maybe I'm thinking of it as an n squared by n squared right now. B11, Bn. So these are your inputs to your circuit, and you are trying to compute their product. And one natural thing is to, because the output A times B is bilinear, what you would do is compute bilinear forms and add them up for each one of these. So this will be somehow the sum of some. So here we'll have some product gates, maybe with coefficients. And each one of these will take a linear form here and a linear form here. So these are, when I write sum, I mean a linear combination. Okay? So the question is, in bilinear complexity in algebraic circuits, is how many multiplications do you need in order to compute matrix product? Okay? The way I wrote it here, so let's say we have 1, 2, up to R. The way I wrote it here, clearly R is at most n squared, n cubed. Strassen sort of shocked the world 40 years ago, showing that R is 2 to the, n to the log base 2 of 7, which is less than 3. And then there was a long list of improvements. Where is Don? So Don is responsible, Coppersmith is responsible for one of the, almost the best improvements until a decade ago, and then some people improved the last, so I'm not sure what's the best known, but we know something like n to the 2.3, and then there are various improvements in the third and fourth digits that are recent. Anyway, so we don't know, for example, that this doesn't go down all the way to n squared, or just n squared times some polylog. It's a great open question. So where is the tensor? You see the tensor. Everybody sees the tensor. These are things, if you just think of not this view, but this view, where this guy is feeding to, right? Then you get a tensor, right? It's a product of three linear forms. And in fact, this tensor is very explicit. What's the matrix multiplication tensor? So you can think of it, these are n squared, n squared, n squared. And this matrix multiplication tensor simply would have in positions ij, or maybe, I don't know, ik, kj, ji, it would be 1 and 0 otherwise. Right? So that's a tensor, and what you are trying to understand is its rank. We'll see how this point of view is interesting later when I show you Spilka's law bound for this matrix multiplication tensor. Okay, so that's the second motivation. Just understanding this tensor is already important enough. I just want to mention mixtures. Where do tensors come up in nature? So in general, I mean, if you are a machine learning guy or you go to a machine learning talk, they tell you that natural distributions are not so complex, and even in high dimensions, they are not as complex as you might think. Usually, there are a few parameters describing them, and you're trying to understand these parameters. The typical story, which goes back to papers in biology a century ago, discovering that certain natural distributions are not Gaussian, but mixture of a few Gaussians. Like maybe the height of people, is not quite a Gaussian, but maybe it's a mixture of Gaussians if you consider the distribution for men and the distribution for women. Or you can do all sorts of things like that. So you would like to give you a distribution or samples from a distribution, and you would like to know, to describe it as a mixture of simple distributions. And for us, for tensors, the mixture is going to be of product distributions. If you are in d dimensions, then what you should think about is a distribution that's a product of d independent variables. This is exactly what's written here. So for example, if you have a distribution P, and it's a mixture, these alpha I sums to 1, and they are non-negative, Pi, and each Pi is simply a distribution, something like U. Yeah. Well, is of this form. Yeah. I'm not consistent in my notation, but anyway, you understand. Each one is, these are themselves distributions on single objects, and it just takes a tensor product. If the description of P is just a tensor, this corresponds directly to a tensor, and this decomposition corresponding directly to its rank decomposition. So I should have said we are interested in matrix rank and in matrix decomposition, which is finding out this decomposition into few rank 1 tensors, right? So if I gave you a distribution that was generated this way, asking for the rank and for the decomposition is really asking for the, how it looks as a mixture of independent random variables.
But here you insist that the rank 1 are non-negative, right?
Yeah. That's a good point, and it comes up. You have to.
If you don't insist,
then you can get negative, and it will not give you what you want.
Get better if
No. It's a hard problem. We don't know. I mean, all this problem, like I said, it's NP hard. I'll tell you a little bit about what's known. There are lots of heuristics or algorithms provable that work under certain conditions. You'll see one. Not for this, but for the general rank decomposition. Yeah, but this is, I'm just motivating it. It's a big question. Also, the tensors, you can think of them as just the third moment of some distributions, some multidimensional distributions that you can get by sampling. So you can just sample, and the average will be your tensor. it will be close to the real third moment of the distribution, or this moment of the distribution. And you can try to use this for various things. In fact, it is used to, for example, learning mixtures of Gaussians. Okay, so that's these are the mixtures. And the last thing I'll probably talk about at the end, if I get to it, so quantum, so basically tensors in d dimensions correspond in a natural way to d-partite over the complex numbers, correspond to d-partite quantum states. And their decomposition is more or less like here. You would like to get them as a mixture of tensor products, a mixture of simple tensors that are generated by. So there will be d parties. Each party holds a piece of a quantum state. If it's a product state, then you are in rank 1, and if not, you are trying to, for example, decompose it to a sum of simple states. And we'll see another problem related to this if I get to the end. Okay, so these are motivations. I didn't want to spend much time about this, but and there are lots of just tensors arise. Again, machine learning and statistics are full of tensor and tensor rank and tensor decomposition problems, and tensor completion problems. All this Netflix challenge and all these similar questions arise there, and topic modeling and many others. So let's skip that, and you can get a lot of it in machine learning talks. Questions so far? So now I want to show you some results, and actually maybe part of the introduction, maybe the introduction stops here. I just want to talk about border rank and so in some sense, if you are an algebraic geometer, and even if you are not, border rank is a notion that makes a bit more sense than rank, because of the following. So basically, you can think of all the tensors. Just look at all tensors of rank R, T, such that rank of T is at most R. What is this object? So it lives into the d dimensions, and this set of points there. Is it nice? Is it a nice algebraic variety? Well, the way to study it is to understand which polynomials vanish on this set. So maybe you can call it VR. Which polynomials in this into the d variables vanish on VR. It's a very important question. If you had such a nice characterizations of the polynomials that vanish on TR, you can tell what the rank is, right? You can just test all these polynomials or generators for these polynomials, and you know whether your tensor has rank R or not. And moreover, in dimension 2, so for d equals 2, the answer is yes. Yeah, this is a VR is a algebraic variety. How can you describe all matrices that have rank R by polynomials? Which polynomials will we test in order to see that this matrix? In the variables are just the entries of the matrix. Which polynomials will you use?
Subdeterminants.
Yeah, subdeterminants. You'll pick every possible R plus 1 by R plus 1 minor, right? If this is M, you look at the determinant of M as T, where these are sets of size R plus 1, R plus 1, and demand that this is 0 for every such choice. right? So in fact, in dimension 2, it is an algebraic variety, so the set is nice. But when D goes higher, that's one source of the problem. When D is larger than 2, then it's not an algebraic variety. So you can make it an algebraic variety. How can you make it an algebraic variety? Consider all polynomials. I don't know what to call them. We can call them. It's not important that it has a name, but P sub r, you could say all polys that vanish on the smallest set of polynomials that vanish on V sub r. And then you can define VR bar to be the 0 set. And this will be an algebraic variety. So you'll get more points.
How does it fail to be a variety? It's not finitely generated? Or?
This? No. No, so let me just, yeah, it fails to be an algebraic variety. Yeah. Yeah, I will, but just give me a second. I will give you a simplest example. I just want to, so this, that's what's called the Zariski closure of this set of points. Doesn't matter that you know the definition, because there's another definition of this set of zeros of these polynomials, which is just, you look at limits in the Euclidean topology. So you look at the set, so VR is also the set of all T, such that there exists, so every T such that there exists a family T epsilon, such that T epsilon approaches T as epsilon goes to 0, and the rank of all these T epsilons is at most R. So it's not just the low-rank tensors, there are also limit points of low-rank tensors. And here is the simplest example. Hope I get it right. So that's a three-dimensional tensor. This is in the front and this is in the back, okay? So this has rank 3. It's very easy to check, I mean, just by hand, okay? But I want to show you that it's a limit of rank 2 tensors. And here it is. Here you put 1 over epsilon 1, 1 epsilon minus, sorry, I'm missing dimensions. And it's the back tensor. The back tensors look like this, 1 epsilon, epsilon, epsilon squared. So you agree this rank is 1, right? I mean, this matrix is a scaling of this matrix. Minus this tensor. So you have zeros, you have zeros, you have 1 over epsilon. Okay? And you can see one of the problems is that, why this is not Zariski closed and this is in D equals 2 is Zariski closed, is that in matrices we have, from the eigenvalues, we have sort of a bound. If we approach something, we can actually know if we are close enough. That already is in our set. But in tensors, that's not true. And you can see the reason it's not true is that this blows up. There's no boundedness or condition restricting the norm of these elements of this sequence.
Sorry, I'm really slow. Why is that first guy rank 1?
This guy. You agree that this guy is rank 1? This matrix, as a matrix.
No.
Okay, so you can check it.
Sorry, what?
Determinant multiply the first row by epsilon.
The determinant is 0. That's a very good way to see it. Okay, so you can figure out the decomposition if you want. That's a very good point. Yeah, it's easily rank 1. You have to put 1 over root epsilon on the, yeah, it doesn't matter. Okay, so that's the example. So what do we know about border rank? So this, you can look for a tensor. Now we have another notion. What's its border rank? Is it a limit of lower rank tensors? And what do we know about this? So obviously, so let me call it B rank. This is the border rank of T. So you understand, it's a minimal decomposition into. It's a limit. It's the smallest R, so that it's the limit of rank R tensors. And so it's of course it's at most rank of T. And here is a question. This great open question. Is it always bounded by, that's the first of many open questions. Okay, we don't know that you can bound it by any function of D times the border rank. The best we know is the result of Jeroen in terms of a lower bound. So there exists tensors Tn larger and larger, such that the rank of Tn over the border rank of Tn is at least D, maybe minus. Okay, so you can approach a ratio of D. But we don't know an upper bound for this. Yes?
So do you have any algorithm for computing the ideal of VR?
No, nobody knows. I mean, very, very few polynomials that do not arise. You can get polynomials in VR, in PR, simply by flattening and that's what lots of algebraic geometers do. You flatten, take a linear map, and then take the subdeterminants. We know other polynomials in this only for constant size tensors. Few, very few. And it's hard to get equations. Yeah. Okay. So that's, I think, all I want to tell you about border rank.
Well, like, even if you did, that wouldn't solve this
problem. No, it wouldn't solve this problem, but it's a great question. I mean, one natural approach to studying tensor rank is to prove lower bounds for lower bounds. To characterize this ideal. Maybe I'll just say one more thing, is that, matrix multiplication, I mentioned it as a very basic and important tensor that we like. It turns out that for the complexity of matrix multiplication, it's sufficient to understand the border rank. It turns out that if you have, just 100 by 100 by 100 matrix multiplication tensor, and you can prove an upper bound on its border rank, then you already have an algorithm that computes matrix multiplication asymptotically with this complexity. And one way to say Strassen's old result was that the border rank of the matrix multiplication tensor, when you talk about 2 by 2 by 2 matrices, is at most 7. Now the fact that the rank, he proved actually that the rank is at most 7. So that's a strong, he proved a stronger result. But what took time to discover, Landsberg, is that, if it was 6, it would be a better matrix multiplication exponent, but this is tight. Okay, and this, Yaim, this needs understanding the polynomials in this variety. That's a way to prove this law. Okay, so questions so far?
Does this matter if you're in characteristic P?
Yeah, it matters. It matters a lot. I didn't say various things, but anyway, for these results, they are usually over the complex numbers, or not. It's very interesting to do it over any field. You missed my first couple of sentences, but all fields are interesting. Some of the results hold for only some fields. This we understand, but you'll see lower bounds for matrix multiplication over F2 soon. I mean, in the second part. It matters a lot. One thing another weird thing that is different than matrices and dimension 2 is that in the matrix case, the rank over a field does not change when you go to an extension field. Does not get smaller. For bigger than 2, it does. There are simple examples that I will not show you. Okay, more questions?
Can I just make a comment?
Yes?
We don't know this are the fields in positive characteristic, but we also don't know a relationship between the border rank of the matrix multiplication and an algorithm for matrix multiplication.
Yeah, in finite characteristics. That's right. Yes. Yes.
We do know.
We.
If the field is large enough, you just interpolate and do interpolation.
No, I
Same
mean,
trick.
but that definition might not hold anymore.
Yeah, I'm not sure that. Yeah, I think it's a fair comment. But anyway, this was for complex numbers or real numbers. Okay, so I want to start show you some results. Now, just I picked things which have really nice ideas, and maybe some of these ideas are useful for more powerful results. So the most basic question, one basic question. Is I give you a tensor T, and you don't know it, but it has rank R. In fact, let me do it just in the case of 3. Okay. I'm now moving to this. Many of the things I'll show you are for dimension 3 only. Some have extensions which I will not tell you about, but suppose I just gave you AUI tensor VI tensor WI. So suppose you know it has a decomposition with the rank R matrices. One question you can ask is, when is this decomposition unique? Now, what do I mean unique? Of course, it's clear that the general linear group acts on every side of this tensor, right? You can change basis, and on every side, on every dimension, the rank wouldn't change. Of course, you could permute the order of this summation, and it wouldn't change. So, but up to this, is it unique? And here's a condition that came up. I mean, this guy didn't write a paper. Somebody wrote a paper that mentions that he did it. He wanted to give conditions when it is unique. And in fact, his argument will give a decomposition. I want to show you this. So such that this set UI and this set VI are linearly independent. And furthermore, set WI does not contain parallel vectors. Okay, so these are the conditions. They are clear, right? I mean, so it's a special case. It's a very special case. Then the decomposition is unique. And in fact, the argument shows that it can be found efficiently by a probabilistic algorithm. So let me show you the algorithm, and it's the fact that it works will actually prove uniqueness. Okay, the statement is clear. Okay, I need to start erasing stuff. So I'll not give you all the details, but as I said, it's linear algebra, so you will be able to complete what I'm missing. Yeah, so this from memory, but I hope I'm not forgetting any subtle points. So what's the idea? Yeah, you are trying to, I give you T, and you're trying to come up with this decomposition. So this decomposition. So let me call just U will be the matrix whose columns are the UIs, and V VI. So it's an n by R matrix. We are trying to figure out, and this notation is useful if we are doing the following trick. So what is a tensor? A tensor looks like this, right? So maybe here sits the U's, here sits the V's, and here sits the W's. One only thing we know how to do is linear algebra. We work with matrices, so we are trying to generate a matrix out of this tensor. And a really nice and simple way to generate a tensor matrix is just to take a linear combination, let's say in this dimension. So pick A at random. It will not, okay, I'm not sure over which fields it will work. This will follow from the, it was originally done with, over complex numbers, and you pick a unit vector at random. But anyway, pick a random vector. So let me write it R here. This means at random, uniformly at random. And let's look at this linear combination. So it will be a matrix, which is the sum of, at every point. So this matrix at positions ij will take the sum over k, and here times k sub k. Right? So what happens? What is this matrix? What does this matrix look like if we knew the decomposition? I claim that this is simply we can write down the decomposition. So this sum over R, UI, then the VI. And here we have simply omega, so I, yeah. The inner product of the i's omega with A, right? That's a linear combination. So symbolically in these terms, what we really have, if we denote D sub A, a diagonal matrix, where in the ith diagonal term we simply put WIA, okay? Then I claim that this equals U D times dA V transpose, or dagger, if you want, right? It's just another representation of the same thing, okay? So we don't know U and V, but we are given this matrix. So we would like to sort of compute its left and right eigenvectors, and then we will be done. I want to point out that already here we are using condition 2. What is condition 2 says that no two vectors are parallel. This means that with high probability for a random A, all these entries will be distinct. So let's assume that they are distinct. So that's important. So what we are going to do, I'll tell you how we are, the steps to uncovering the information that we'll find the UIs first, and then we'll find the set of VIs, and then we'll match them, because we have to know which U goes with which V. And all will be simple, and then we'll find the WIs and mesh them, which is right. This is what we need to do. So I mean, it's sort of problematic to compute the left and right eigenvectors. So in fact, Henrich's idea was a little more involved than this. Just do it twice. So let's say we are now doing this. So also take B at random, and also compute the same. So now we have compute also U dB transpose. Now we have two matrices. That's really nice because compute AB inverse. So what is A? This is A, and this is B. Compute AB inverse. How does AB inverse look like? Well, I'm sure you'll jump that it has no inverse, take pseudo inverse. I'm not going to go into this. It, of course, will have no inverse because it's low rank. But we don't really worry about this. This looks like, if inverses existed, this will be U dA V transpose V transpose inverse, which cancel dB inverse U inverse, which is just U dA dB inverse U inverse. And that thing we know how to decompose. You just find the eigenvalues, you know the U's. Okay? So good. And this is not really a problem. So anyway, so that's how we found the UIs. Right? How do we find the VIs? Same thing. So we can compute also A inverse B. I guess we need to take transpose of this. And this will be the same. So this will be V dA inverse dB. V inverse and you can find this set. Okay? Again, eigenvalue decomposition. How do we match them up? Anybody? Well, which eigenvalues will correspond to which eigenvector? Look, the diagonal matrix here and the diagonal matrix here are the inverse of one another. So the matching is just by the eigenvalues. Okay? The one with the eigenvalue alpha will match to the one with the eigenvalue alpha inverse. So, so this is by matching eigenvalues. How do we find the WIs? Yeah, it's linear algebra now, right? We have everything we need. We have T equals now summation UI tensor VI, which we know tensor WI. Right, so this we know, and this we don't know. So it's a linear system. We just have to make sure, oh, it's not just a linear system, it's a linear system that has a solution, because that's how we started. It's a linear system that has a solution. So we just want to make sure that the equations in the linear system we generated are linearly independent. And for this, we have to use condition 1, which we didn't use yet. And one way to see that they are linearly independent is simply by mentally mentally changing basis. If you take U, the matrix U, you take a linear transformation, let's say R, which takes U to this matrix. So this R, this is R, this is 1, 1, 1, and 0, 0. And you do the same, maybe S does it the same to the matrix V. Right? So just change basis, so these are diagonal vectors now, they are unit vectors, R of them. And then with my T prime is whatever, RTS. So change basis here and change basis here. What we get is that this linear system really looks like this matrix times W1 in this direction, this matrix times W2. In short, there are disjoint conditions. We can read off, after this change of basis, we can read off W1, W2, etc. from T prime. Right? So that's, Okay, questions?
So the randomness is in knowing the eigenvalues of
Yeah.
discrete.
Yeah, that's the only purpose for the randomness.
And we don't know typically randomness.
I don't know that anybody looked at it. It's probably not hard because you could, in fact, it should be easy. There should be a simple polynomial family of vectors A and B that will, that's a good point. You can de-randomize it. But this condition is important. Okay. More questions? Okay, so just last few minutes, when we'll take a break, I want to tell you a better condition for uniqueness, which has advantages and disadvantages, and it leads to the first lower bound we'll see that is better than, than n. This is used all over the place in machine learning, this algorithm. And it was discovered, I think, independently by many different people. But it's just beautiful. So I want to tell you about Kraskal's condition. For uniqueness. Again, I'll do it for the case of dimension 3. There are extensions for higher dimensions. And for this, we need the following. If I give you a matrix U, you can think of U as the same thing, the UIs that appear in the decomposition. So this is n, and this is some. I want to say what is the independence number of U, the maximum number k, such that every k columns are linearly independent. Okay? Very basic property of matrices. So here's the Kraskal's condition. If I'm consistent with my notation of theorems, Kraskal. So assume we have a decomposition. So T is again the sum over R UI though VI and though WI. And the matrices UVW are defined as before. And assume that R is smaller. I guess if I add smaller will be good. Smaller than 3/2 I of U plus I of W V plus I of W. Okay? That's a condition. That you have enough independence, that you don't have too much. Yeah, you have enough independence relative to the rank. So that then what you get is that the rank of T is R, and this decomposition is unique. The proof of this is, okay, everybody understands the statement. The proof of this is combinatorial and clever, and I'm not going to show it. But I want to point out that it's non-algorithmic. It would be really interesting to have an algorithm to find this decomposition efficiently. We don't know. But the one obvious consequence I want to show you is that finally we can see a tensor whose rank is bigger than n just directly from this condition. We can take U equals V equals W. So I'm going to give you a tensor. I'm going to give you its decomposition. As my uniqueness, it will be. So R will be 3/2 n, maybe -1. 3/2 n. No. R will be, something like this. And here is what U is. You just take a van der Monde matrix. So here put some 1, alpha I in position I. Alpha I squared, alpha I to the n minus 1. Take this van der Monde matrix. What do we know about it? Every n columns are independent, right? Good. So its independence number is n. R satisfies this because we have n plus n plus n, 3/2.
You want 1/2 instead of 3/2 there?
Yeah. Thank you. 3/2 when I thought of all of them as n. Yeah. 1/2. Right, so this tensor, so if I take U equals V equals W and I just define this tensor, it's very simple, very explicit. It's just the sum of UI, tensor V, tensor UI, right, with this U. Then I claim by Kraskal theorem that rank of T is at most 3n/2, maybe minus. Right, so we have finally seen a tensor whose rank is bigger than its size, its side. And then immediately after the talk, I'll show you a much better lower bound, much better, twice as large, of Spilka. So questions about this? Okay, so let's take a 5-minute break. And, outside? Anybody else outside? No? Yeah, any baby outside? Okay. So I want to show you a result of Spilka, again from about 15 years ago. We are going to go to the matrix multiplication tensor, so maybe n will become n squared now. We want to beat n squared. So we are going to look at the field F2. Everything I'll say is about the field F2. Although there are results like this for every finite field, and in fact for every field, but some of them are slightly weaker, so I'm not going to go into this. And we are going to look at the matrix multiplication tensor of n by n matrices, and the rank is going to be okay. So this is twice as good as the previous lower bound. And not only is it twice as good, that's the best we know. We don't know how to beat the factor 3 for any explicit tensor. There are other lower bounds for other tensors that are roughly factor 3, and that's it. That's the best we know. And just to prepare you for this last thing, or the next thing, is that most methods we know how to prove lower bounds for 3 tensors will not yield better bound than 6 times the size. So it's, I don't know if it makes it more impressive or less impressive. But this method that Spilka will use will not fall in the barriers, as far as I know, that I'm going to show you. That potentially it has limits to go to maybe superlinear lower bound. Okay, right? This is a linear lower bound because n squared is there. So what it's proving is actually a stronger bound. So let me tell you here what it's proving. And it's a beautiful idea, and it's a concept that I don't think was explored after he introduced it for this paper. And this is the idea of matrix codes. So what's a matrix code? You just simply want a linear map, C, linear from the set of all n by n matrices over this field to vectors of let's say length r, because r will be eventually the rank. And it should satisfy, so again, you can, in your mind, you can extend it to any field, but I'll just talk about F2. So this map is really, the entries of this map, the R entries are, U1 times, if the matrix here is, so basically a matrix A will go to U1 comma A. Or should I, so that's my notation. UR. Right? So you think of A as a vector. It's just linear forms in the matrix, right? So that's a code. When is it a matrix code? I mean, it's just a linear map at this point. When is it a matrix code? It's a matrix code if rank if rank K matrices, what do I want to rank S matrices have weight at least n times S. So what you want, it's a matrix code, and for every A such that rank of A is S, you want that the Hamming weight of CA is at least n times S. And this holds for every S. So maybe I should write for every S, for every A. So you want that matrices of high rank will have lots of non-zeros. And this, because the map is linear, you see that this also implies that for every A and B, every two matrices A and B, the distance, the Hamming distance between them, Hamming distance is of C of A, just as, think of them as real codes, is at least n times the rank of A minus B, right? Just by linearity. That's a property one. That's a matrix code. And what he actually is proving, Amir, is that for every matrix code C, R is at least 3 minus D01. Just this property alone guarantees that the image has to be large. This R, the number of coordinates in your code, is large. Why? What does it have to do with this? So I'll prove this, but let me just tell you why. Any circuit, so any tensor rank, upper bound on the matrix multiplication tensor, it gives you a code. So let's assume that rank of this tensor was at most R. And I want to derive from it a matrix code of size R. So how do you do it? It's really simple. So remember the picture we had before. We have maybe two matrices X and Y. So these are the their entries, and we are generating here the matrix X times Y. And having matrix the tensor rank being R means that there are multiplication gates in this circuit. And each one of these, let's say the ith one, is really UI of X times Vi of Y. So this gate computes UI A or X Vi Y. Okay, this circuit computes. Okay, so you have this, you are given this. So what is the matrix code now? the matrix code will be, so C will map X, or matrix, let me say, A, to, you just forget about the V's, you take the U's in this decomposition. That gives you your code. U1A, that's your code. Now we want to see why why this is the matrix code. The definition is clear. It's just a linear map, right? I mean, just linear functions here, so it's a linear map. Why is it a matrix code? Because assume that the rank of A's equal to S. Think about it. So we didn't use anything about matrix multiplication yet, so we should. How do we use the fact that matrix multiplication? Assume, look at these things. How many of these things can be zeros? We want to prove that, this image of A has high weight. It has lots of ones. Assume that it has less than n times S ones. Everything else is zeros, right? When you do this multiplication and this was a 0, nothing will depend on y. But how many possible outputs do we have if the rank of A is S? How many possible outputs should there be here?
S rows that are
Yeah, at least, right? So the image of A times y over all y's is at least 2 to the ns, right? So it should have at least, this many parameters, right? We can take all base changes or something, right? So it has to be at least. On the other hand, this number is also at most, maybe I want to write it. Let's put rank of A is here. Rank of A is S, but this is at most 2 to the weight of A, of C of A, sorry. It's just that, it's just that more, the way y can make changes in this part is only at the ones, so it's at most C of A. Okay, is this clear to everybody? Yeah, it's simple. Very simple. So we proved this lower bound, right? And in fact, we proved a little more. It's not just that we found lots of places which are non-zero here. We found at least ns many for which the UIs are linearly independent, right? If the positions in which these are ones, so I claim something stronger follows. Right. NS of the UIs, they're at least NS linearly independent UIs such that UIA right. Again, if there were fewer, it's really what determines the image is the number of linearly independent ones, right? I mean, if there are dependent ones, Y will not affect them in any other way. The map is linear. Okay, so you can remember this for a little bit. Okay, but basically it proves that it's a tree code. So all we have to do is prove this lower bound. And I'll do it in 2 steps. First, I'll prove to you that R is at least 1 times n squared. And then I'll prove to you that R is at least 2 minus little of 1 n squared. So we'll do it. So each one of is a trick. Well, in fact, the first trick, okay, everybody, that's all we need to show is a lower bound on the length of a matrix code. Well, I claim that this we already proved. Why? That R has to be at least n squared. Well, in the weight of a non-singular matrix, right? S is n. So we have to have weight at least n squared. Well, you have to have at least n squared coordinates to do that. Yes? So now we come to the tricks. And the trick to get the second one is the Plotkin bound. This is a basic lemma in coding theory. So the Plotkin bound. Basically, what we used to get the first result was just using one matrix A. In order to prove better lower bound on R, we'll use several matrices. The Plotkin bound just says in general that if you have vectors, I can call them A's, A1, A2. No, it's the C of A. So just vectors V1, V2, Vt, F2 to the R, and the Hamming distance between any two of them is at least D, some number D. So they are all pairwise distinct in this many ways. Then R is at least basically 2 times D, sorry. And you lose something like D over T. So if you have many, you lose. So it's basically a factor of 2. Okay? It's a simple thing to prove. You can prove it at home. And how do we use that? Well, if we could find T, if you could find many matrices, right? Here we used just one matrix, which was non-singular. Right? This should be true for all ij. So I claim that all we need is many T matrices AT such that AI minus AJ is non-singular. Different than 0 is 1, but right? If I have this, then we know that these are the vectors we are talking about here, and D is n squared, right? Weight, yes? These vectors Vi will be simply the code of AI. Right? So every pair of code words have to be distant n squared apart, and question.
You also try to just get more matrices so the difference is high rank.
No, you could, but it wouldn't help. You can't squeeze this lemon more than Amir did. Okay? So all we need is more matrices. So how do you find them? If we find them, then we can get this second lower bound. And you notice, you just need this to be a super constant in order to get a factor 2 lower bound. And here's the idea. It's such a clever idea. And then we'll milk it some more, as you'll see. So consider we want this to happen. So just let's look at the following polynomial, P of say, x1, xt. These are matrices, n by n matrices. Think of them as variables, right? And let's just write down the polynomial that ensures that all their differences are non-singular. So it is a determinant of the product I if this polynomial is not identically 0, then we have our, right? We have the matrices we wanted. Okay? So why is it non-zero? Anybody sees? I mean, for what t can you do it? So the claim here, the lemma is really that for every t, in fact, less than 2 to the n, this polynomial p is not identically 0. You could take a huge number of matrices. We don't need them.
You can take the finite field of
Very good.
Yeah.
Yes. The proof is like this. You don't need all your matrices. Just take those that arise from a finite field. So there's a natural embedding f of 2 to the n into right? I mean, yeah. If you don't know it, you can figure it out yourself or read about it. It's very simple. So there's such a linear map. But except for the 0 element in this field, right? All of them are mapped to non-singular matrices. Why? Because, so this linear homomorphism. Because they each have an inverse. Okay, so these are, so that's a proof. Everybody happy? So we did this. Now how do you do the last one? It's another trick, and the trick here says that until now we lower bounded R, right? We put a lower bound on R. So in fact, this lower bound will actually come from this lower bound in a very simple way. We can put here r minus n squared roughly. So then it will be the same. If we prove this, then we are fine. So that's what you'll see. So you want to say that you really don't need to consider all the coordinates in R. You don't need, you can throw out about n squared of them, and still it is a matrix code for a purpose. And still you can find such matrices A1 through AT. So why is this true? Let me give you a simple lemma, and this is a generalization of this lemma. Okay? So suppose you have any polynomial and the degree of Q is D. I mean, this, so this is a lemma. Then I claim that there is, and suppose it's not identically 0. Then I claim that there is an assignment which is still non-zero on this polynomial. This is true over every field. There is an assignment to these variables of weight, Hamming weight at most, D, that still makes it non-zero. So there exists, let's say, alpha vector, weight of alpha, Hamming weight. So at most D and P of Q of alpha is not 0. What's the proof? Take here any monomial. So any monomial xi1, xi, at most D, right? I mean, take any monomial that has a non-zero coefficient. There must be some. Okay. Set everything so alpha I is going to be 0 if, well, this is, maybe I should write it, pi I in S xi. So alpha I is 0 if, I is not in S. So the polynomial after this restriction is still non-zero, right? So it has a non-zero assignment. Take it. That will be the completion of your alpha. Okay? Yes, everybody? So it's zeros outside this set, and inside this set, whatever it is. Okay. That's very simple. So what's the connection to what's going on there? These zeros that I put, saying the weight is is small, namely lots of zeros, it's just a choice of basis. We could have chosen any number of independent linear conditions on these variables and demand that they would be non-zero. So here we got m minus d, at least m minus d, so out of m linear independent linear forms, there exists a non-zero assignment which kills at least m minus d of them. Right? So let's get back to our polynomial here. This polynomial. We already know that by this little observation over there, that there are at least n squared independent linear forms among the R linear forms that we are given, right, in the code. So just focus on them. They are the n squared linear forms. What is the degree of this polynomial? Right? N. If it was n squared, would be bad. N, right? Okay, good. So we know that we can kill n squared minus n times t choose 2 of them by such a collection of AI that whose differences are non-singular, right? And what we are proving, what we proved just before here, is that whatever remains has to have length n times, 2 times n squared. So all in all, combining this, we get that R is at least 2 minus, so what did we get here? It was n squared over t. You'll see the trade-off. I'm omitting constants. Right, this is what we lose in the first argument. That's what we lose in the second argument. And you can take something like t to be n to the third, and you get that R is at least 2n squared, 3 n squared minus n squared. Isn't it beautiful? What?
Is the 3 tied for this lemma, for the code?
It's a good question. I'm not sure. Good question. Okay, so this is the best lower bound known in any field, in any. All right. No questions? I'll move on. Okay, the last thing I want to talk about is barriers. Barriers to lower bounds. This is based on work of Fremenko, Gog. that we did last year. So we can prove lower bound, and it's by now sort of part of the important part of the field to find excuses. So everybody working on circuit complexity, algebraic complexity, knows the frustration of trying to prove non-trivial lower bounds. And in our despair, we turn to excuses that explain why we did not succeed yet. So what are excuses? You take the collection of techniques that were used to prove the existing lower bounds, and you say these techniques cannot yield better or much better lower bounds. So this was done all over the place. People who heard about natural proofs, these are, for Boolean complexity, Rasborov-Rudis, these are very good excuses for why we can prove Boolean lower bounds. Even before there are diagonalization and algebraization excuses of a different form on lower bounds for Turing machines. And all of these somehow have conditions in them. They are, it's not that they rule out proving lower bound, but if you prove a lower bound, let's say in the natural proofs case, you would prove something extra, you'll get a side benefit, for example, of a fast factoring algorithm. So if we believe that there is none, then it's hard to prove lower bounds. Similar things were attempted in the algebraic complexity case. So there are assumptions you can make under which there are barriers to proving lower bounds. I'm not going to talk about this. I'm going to talk about this result because it has no conditions. This is an absolute barrier to a certain family of attacks. And this family of attacks is exactly flattenings. Okay, so I want to say by flattenings, whatever flattenings, not just these trivial ones, but by any linear forms taking tensors to matrices, you cannot prove much better lower bounds than the lower bounds we've seen here. So I want to define this family. So what are rank methods or matrix rank methods? Proving tensor rank lower bound. What you are allowed to do is to take any mapping which is linear from the space of all tensors, F. The matrices can be arbitrary in size, okay? And further, you prove that for any simple vector, so it's, I erased it, but simple tensor, rank 1 tensor, so let's call this set S, set of all U1. All the rank 1 tensors, so they are simple. L of t is at most some R1 because it's for 1 tensors for all. Suppose you somehow design your L so that it's like that. And suppose further that you found the t, so now find rank, L of t, so should be rank here. So this is a matrix rank, right? Matrix rank. So you map all simple tensors to low rank matrix. And suppose you found some t, so that the matrix rank of L of t is big, t. Then I claim that this immediately implies a lower bound, right? So the rank of t, the tensor rank of t is at least t over R1. Right? Because by linearity, right? You were adding simple, t simple tensors, each one, and rank is subadditive. I should say that I'm showing you this for tensor rank, but this method, this flattening, it's a natural word in the case of tensors, but I mean, it's a prevailing method for proving arithmetic circuit lower bounds. By far the prevailing method, a very successful method. And it proves really so amazing lower bounds. And in this context, the simple objects, the simple polynomials are not rank 1 tensors, but other simple polynomials. For example, if you are proving depth 3 lower bounds, so you are proving lower bounds on circuits of this form. Here are the variables. So these are depth 3. Then simple, you just want to say that you need to add up many depth 2. And depth 2 are just products of linear forms. So it's very similar to tensors, only the symmetric case, so products of linear forms. So here simple is product of linear forms. And there are exponential lower bounds known for these. And there are also a set of very powerful lower bounds recently by starting with Niraj Kayal and then a whole slew of them. You want to prove lower bounds for depth 4. And here the simple are sort of sparse polynomials. Right, so anyway, simple is what it is. Things like that. You assume your circuit is small. Yeah, they basically do exactly this. They are extremely clever methods. These are based on partial derivatives of your polynomial. These are based on shifted partial derivatives, so differential forms. And there's intuition for algebraic geometry, for choosing them. And it's just beautiful stuff. And then so this method is successful for proving almost everything we know. And I want to say the theorem here in this paper is that well, maybe I'll just say it under this assumption. So if we are given such an L such that the rank of T of L of T in S is at most R1, then the rank of, then for all T, rank of T is not much bigger than what we get by the trivial lower bound. So it will be R1. So R1 will just, in the ratio, here we take T divided by R1. R1 will cancel. And here we get 2 to the D times n to the D over 2.
Rank of L of T.
Yes. Thank you. And for the rank of T, we divide it by R1, so we cannot get lower bounds that are better than this small factor than the trivial lower bound. Okay. Yeah, so it means we should step out of the comfort zone and maybe use techniques like Amir or, I don't know, maybe there are not enough proof barriers for them, and so on. Okay, so I want to tell you the idea here. So everybody's happy with the statement. So again, barriers really often look like this. You want to prove a lower bound, but the barrier gives you an upper bound. An upper bound is often, for complexity theorists, is a lower bound on a lower bound. So how do you do this? So it's simple. It's just a simple linear algebra argument, but there is something subtle about it. There are basically 2 steps. You move from a function which is about tensors, about constant tensors, tensors over the field, into symbolic tensors, tensors of polynomials. And you look at what the map does to them, and then you get more structure because you are working with this nice object, the ring of polynomials, and you derive part of the bound from there, and then you go back to the constants. So let me, in the 15 minutes, I wanted to say 5 minutes at the end, something about quantum. So let's see what I can do. Okay, but I'll explain the idea. I mean, the idea is simple. So we know this. And now we want to move to polynomials. So think of what this map L will do to a generic tensor. So apply L. So we'll call it this M of x. So we are going to now work in a field where, so the vector x is x1, xd. So we'll have dn variables, and each xi is xi1. Right? We have dn variables. And we'll work formally. The ring of polynomials will be this. And we'll actually have to look at the field of fractions. So m of x is what? Is L of this tensor, this simple tensor. And, you know, it maps this tensor to these m by m matrices. By the way, one important point I wanted to mention is that we put no bound on m. M can be huge, and in fact, in some of the arguments in algebraic complexity, it should be huge. It is huge. R1 itself is huge, but you still get something. So somehow, this ratio is far, far smaller than R1 in these arguments. You have to really go to huge matrices, and you prove lower bounds that are impressive, but they are, this R1 can be much super polynomial in this ratio. Anyway, and another thing about this is that L does not have to be explicit for this theorem to hold. L could come out of some random argument or existence argument. So what is this map? So I claim it's just a matrix of polynomials, right? Polynomials of degree d in these variables. So this is to write it like this. So these are just matrices times x sub b, and x sub b are just so it's just if you should think of E as a vector that selects which. So this will be not just a multilinear polynomial, but it will pick one variable from every group. So this vector of exponent will be, so xe will really look like, so E just encodes the exponent, so it will be really the product of some xi to some ei. Ei is a vector, and it encodes which one you pick. Okay. So it looks like it's a matrix whose entries are homogeneous, in fact, multilinear, set multilinear monomials, set multilinear polynomials, and that's their matrix coefficients. They are huge m by m coefficients. Now, what do we want to do? We want to bound the dimension of this span of matrices, m sub b. Not the dimension, the rank of all matrices in this span. So if C is the span of this M sub E, but I want to say that the dimension of, that the rank of C, by which I mean the maximum of C in C, rank of C, is at most what I said, R1 times 2 to the D and to the. And why will this be enough? I mean, there are many more nodes that are like n to the D matrices there at least, right? But this is a bound on the rank of any of them, regardless of what m is. Okay? And why will this be enough? It's enough because every, L of t is in for every t. Every tensor, the image is contained here because this in particular, some of the matrices here are, the images of monomials, or just, the basic tensors, or of the identity tensors, how do you call them? The delta functions. So this is clear. So if we prove this, we prove this. How do we prove this? Here we use the fact that it's polynomials, and I want to claim, first of all, the following, that the rank, and now we are working over f of x, so over the field of rational functions, of this matrix M of x is at most R1. So we know that the rank of every instantiation is at most R1. And, it's sort of an obvious thing if the field is large enough. If f, I guess if f is bigger than nd, then simple. So that's simple. Okay? So the rank is at most R1. Now we start massaging this. So what does this mean? This means that I can write m of x as a sum up to R1, a g of x That's just what it means for the rank over this field of fractions to be here. The only problem is that these may be rational functions. Now, because of my time, let me say that without okay, so what can you do if these are rational functions? So let me just call them prime. They are rational functions. You can clear denominators. Why can you clear, in what sense can you clear denominators? You take a common denominator, it's some polynomial. You find the non-zero of this polynomial. It exists by this thing. Let's say the constant term is non-zero. And then you just expand, so you get, this is really, sort of, you can think of this as polynomials and write 1 minus some p of x. So now everything here is polynomials, but you have this expression, 1 minus a polynomial. And you just write the Taylor expansion of this. Well, of course, it has infinitely many terms, but you don't care because this is homogeneous of degree d. So what we can really say, this is a sum to R1. Sorry, let me write it like this. It's the homogeneous part. We don't care about degrees bigger than. It's the homogeneous part of R1 g I of x tensor hi of x. And now these are polynomials. And in fact of degree at most d. Right? Because I take here, let's say h is everything times the expansion of this, but you truncate it after d, and then you take only the homogeneous d component. It's a little messy to do it formally, but forget about it. This is it. And now we massage this expression just a little bit to get the first factor of 2 to the d there. We are still in the realm of polynomials. How can this happen? Well, component of some exponent d can arise, well, from this product, from something of size, let's say k here and d minus k there. And in fact, it can arise in 2 to the d possible ways, choosing which monomials you take, which sets of variables you take on the left and which sets of variables you take on the right. So what you can really write it as m of x is R1 some S inside D. You just sort of multilinearize it. GIS of x tensor HI S complement, so D minus S. And we have the homogeneous part. Right? So I do this, and why do I do this? Because now I understand for every S, I understand perfectly well what is this space. So now the matrices, the M sub B, the matrices in, so I'm just say it so. M sub B will be, okay, so either, so take any matrix C in C. I claim that either the row span of C is inside inside the coefficient vectors of all monomials of of all polynomials which are set multilinear of this type. So they just I'm not sure about what notation to use. So this space of coefficients of, so I'm just looking at one expression here, vectors of degree most. So all I'm using is that minimum of S and S complement is at most D over 2, and I take the smaller of the two. Okay, so up to here, this decomposition was R1 times 2 to the D, and now I look at this space. Either the rows of C or the columns of C will be contained in the coefficient vectors of all polynomials of this type. And so this just adds a factor n to the D over 2. So it's not completely, yeah, maybe I did it too quickly, but anyway, it's a very simple argument. What you really want to say is that that all matrices in this collection, you can limit their row span and their column span by a very small dimensional space. And this puts an upper bound on the rank. Okay, so this is a real message, and then you can make it formal. Questions about this?
So if the field is small, maybe we can hope for something.
Yeah, if the field is small, maybe you can do something better, because this argument will fail. You have polynomials that, yeah. So let me just in 2 minutes tell you the last thing I wanted to say about this quantum thing. I mean, I'll just state a theorem, and that's all. Theorem with it's actually from several works, but anyway. A tensor, I said that it can be viewed as a multi-partite state. So we have this T on n to the D. You can think of D parties. So it's I would say it's a pure state. And there is a way to think of this tensor as being held by D parties. Each of them is capable of having one of n states, or a superposition of n states. The best way to write it is to make this tensor just into a vector of length n to the D. It's over the complex numbers. It will have unit norm. And then you look at the density matrix. So this will give rise to an n to the d by n to the d tensor. This is T. It's a matrix. This matrix is a density matrix of the state they are all holding, and the way to view a particular what each player has, or rather the interaction of one particular party with the rest, is just to flatten this tensor, to take it to be, to flatten T, to make it n and n to the d minus 1. If you take T and you represent it in this way so that this belongs to the ith player, so this is maybe, let's call it m sub I. You just represent the tensor in this way, then mi dagger is an n by n matrix, and it describes the entanglement between, it doesn't matter if you don't follow it, it describes the entanglement between the ith player and the rest of the players. Okay? So this is what you get if you take the partial trace of this matrix, for those who know, partial trace with respect to the ith player. So this is the object we care about, or not, I don't know but some quantum information theorists care about this a lot. For example, they want to start from D party starts from a state T, and they want to locally change the state, so each party can really do a non-singular operation on its direction, right? We know that this tensor is sort of a natural operation, is changing basis along any one of the dimensions. They want to change this basis in such a way that all of these guys will equal the identity, or the normalized identity. This is a density matrix, so will equal the normalized n. And the question is whether this is possible. And the theorem that we can prove, I will not write down because I have to rush to. So the theorem is that there is an efficient algorithm to do that, to test whether this is possible, and to actually give the linear transformation that each one of them needs to do so that it will result in this entanglement. Now, why am I? Okay, so that's a result. In fact, more carefully stated, the algorithm will, for every epsilon in polynomial time in 1 over epsilon, will get you as close to this as epsilon in, let's say, L2 norm, assuming it's possible to get it at all, okay, or to approach it at all. Why am I saying this in the lecture about tensor ranks? Because it seems to me that the ability to do this gives you, you can take any tensor. In fact, most tensors you can do this for. It's sort of generic tensors behave this way. Very few of those who came to this talk yesterday know that the tensors for which you cannot do this are in the null cone, and there are few. But anyway, most tensors you can do it to. And then efficiently you can take any tensor and convert it to a tensor in this normal form. It's called a scale tensor, a tensor that's nice. It's in some isotropic position. So you can, maybe if you get it like that, it's easier to find its rank, it's easier to find its decomposition, lower bound, I don't know. So let me stop here. Thanks.